before going to the Fano flashback theory, I'm just going to show you a bit how an output of a quantum chemistry package looks like, just maybe to illustrate a bit like Krishnan said. There are plenty quantum chemistry codes. There are open source ones, there are commercial ones. Some are easier than others to use, some are better than others to use for this or this system and so on. And as I said, usually they are user-friendly, but knowing which code and which method to use for this and that system, this takes a bit of time and a bit of experience. Okay? There are codes like Gaussians, MolPro, MolCast. Those are really the most known, and usually you can do more or less everything with those one, but they are commercial. Okay, and then you have open source one, free codes, and those sometimes you have to play with to get what you want. But even with the commercial, for example, I used a lot MolPro. MolPro is good if you want to compute the first 3-4 excited states, but if you want to go to really high excited states, there are some numerical problems. So then you have to move to another code and so on. So, but as I said, this takes experience. Okay, that's not really what I can explain now. Since I want to compute width, decay width, those are not implemented in most quantum chemistry codes. So you need to chemistry code and adapt it, change them for your purpose, right? So there are, in that case, you want to take open source code so you can modify it and get one nice code that I used and is the quantum package. It's open source, it's free, it's easy to install. And what I like also is that it's developed by someone from my university, so if I have problems, and it helps me. So those are just blah blah. It's not that important, the information. But here, this is the important part. So here, that's the output of a Hartree-Fock method. So it's only the Hartree-Fock part, and this is for neon atom. Okay. As I said, when you do Hartree-Fock, when you build your Hamiltonian Hartree-Fock, okay, your Hartree-Fock Hamiltonian matrix, this one depends on your orbitals. So what you do is that you make a guess of the orbitals, you build it, you diagonalize, you get a new guess, and you do that iteratively until it doesn't change. And this is what you see here. So this is the energy as a function of the guess. So in the first guess, you get minus 80 for the total energy, and that's not really good. And so you get a new guess, you get better, better, and better, and at some point, the energy doesn't change at all. Okay? So that's your energy that you want. Okay? Once you have that, you also have the spin orbitals and the Hartree-Fock energy, and this is what is shown here. Okay? So as I said, that's for neon. So neon, the configuration is 1s2, 2s2, 2p6. And this is what you see here. This orbital here, that's the 1s orbital. 2s, and here you have 2p. So 2px, 2py, and 2pz. Okay? And those here, that's your pseudo-continuum orbitals. Okay? And if you look at the energy, you see that they are positive. So it cannot be the energy of the 2 or the 3p of neon. Okay? So there was a question about how to interpret them. You cannot interpret them as excited orbitals, so 3s, 3p, and so on. Okay? Those, it's more like a continuum state, a continuum orbital. So if you put one electron here, it's like it's in a continuum, it's gone. So that would be neon plus one electron in the continuum. Okay? And here I use a very large basis set with about 100 Gaussian functions. So I have 100 and 9 orbitals. And I really need large basis set because I want to treat the continuum to have the decay width. Because as we will see, the decay goes from a bond part to a continuum. And as we discussed already, our continuum is discrete, but you want to make it as dense as possible. So you want to put as many orbitals as possible. Okay? So that's to illustrate the Hartree-Fock method. Okay? No question on this part? Now I have to reshare this screen. Here. Which one is it? Good. Oops. What did I do? Okay. Thank you. Okay, so now let's go to Fano theory of resonances. And just as an introduction, I'm going to explain what I mean by resonances. Okay, so let's say you have a molecule in the ground state here, and you have the limit here of n plus ground state. Okay, so of course here you have excited states, but we're not really interested in. And you have here a molecule which is excited, right? And here you have, so you have one state here, and here you have your continuum. Okay, so the resonance is like, you can see it as a quasi-bond state. So it looks like an excited state, a bond state, but it's embedded and coupled to a continuum of states. Okay, so if you start from this guy here and you excite to this one, okay, it will stay there for a while and then move to the continuum. Okay, and that's what I call resonance. And the time it stays there here before moving to the continuum, that's the lifetime of these resonances. Or if I turn it into energy, that's the width of the resonance. So this is what I mean. Okay? So this guy will go in the continuum. Okay? So let's take some example of resonances, and I mean there are plenty, but the one we are interested in for today and tomorrow, it's the Auger and the ICD case. And let's take neon because it's simple. So let's say you do neon and you make a hole in the 1s orbital of neon. Okay, this neon plus is really high compared to the ionization potential or the energy of neon plus plus. So it is in the continuum. And after some time, it will emit an electron. So one electron from the 2p will fill the 1s, and you go in the continuum of neon plus plus. Okay, so this part is quasi-bond. This part is the continuum. Okay, and going from the quasi-bond to the continuum, we call it, whoops, damn it, the Auger effect. Okay, ICD, you start from neon plus 1s2, 2s1. Okay, now the hole is in the 2s orbital, 2p6. For ICD, you need a neighbor. And this goes to neon plus 1s2, 2s2, 2p5 plus neon plus 1s2, 2s2, 2p5 plus an electron. Okay, I'm not going to explain more than that for ICD. This afternoon, Len talk thoroughly about it. Okay, so it's just to illustrate what I mean. Okay, so this is the quasi-bond part, and this is the continuum. And going from the bond part to the continuum, that's what we call ICD for interatomic Coulombic decay. Yes.
So my question is, if you come with a photon which will take it to this M star state, then this interference means there are two pathways. One is that without forming the quasi-bound state, you directly detach the electron.
Yes.
The other one is with.
Yes.
It will, however, the width of the resonance will reflect the lifetime of the bound state.
So let me just answer the first question, because I didn't answer I didn't understand the second one, but maybe then it would be clear after I answer. So you can do that and that, or you can do that. Okay.
The energy is E. The energy to take it to the M star is let's say ER.
Yes.
So on resonance, at that, if you come with a photon of energy here, then you could do a direct ionization, or it could be via the resonance.
Yes. Yeah. So if your photon is exactly the energy between this one and this one, you can do that, and at some point it goes to the continuum, or because you have the same enough energy, you can directly go to this one. And now you have two pathways, and they can interfere, and you get this Fano profile. Okay, and the profile that you get depends on if you spend more time here, or if you have more chances to do that than that, and that, or that. Okay, so if you go mostly through the resonance and you can forget about the direct path, then you get this Lorentzian shape. Okay. So I'll answer also your second question, because I was not sure to. Okay, this is it. Yeah. It's hard to answer. It depends on the system. So if there is more, yes, yes. Well, you're gonna have a Lorentzian shape for the distribution of your electron. So what I mean is that, so you, and this, yeah, let's say you measure your cross section as a function of the energy of the incoming. Okay, if it goes through the resonance, you're gonna see something like that, with the Lorentzian shape here. Okay, if both pathways are equally probable, you get something like something, yeah, Yeah, it's not well drawn. I'm bad at it. Even though every night I try to draw a bit, but I'm terrible at it. You see what I mean? Okay. So the shape tells you which pathway you go, or which one are preferable, if there is one preferable. Sometimes it's equally probable, and you get this kind of Fano profile. Yeah. So that was your question, or okay?
There are also some case where the profile is like window profile, window horizons. This come down the cross section.
Yes.
Here you have an asymmetric. The second one that you do is you have a profile like it comes down.
Yeah, well, the thing is, it's very confusing. It can be very confusing because if you look from one paper to another, they don't present things the same way. So sometimes that's true. You see that the observable that you have looks like this, and they say Q equals 0,
Yeah.
the asymmetry parameter, but it's actually this Lorentz shape, but just written in a different way, I think. So it's because you use a reduced unit, and it's the absorption, not the emission, and so on. So it's always very confusing to do that. But the Q parameter is telling you it's the transmission through the resonance divided by the transmission, or the other way around, sorry. The transmission through the direct path divided by the transmission through the resonance. So if you neglect the direct path, Q equals 0. But I always find that very confusing. And discussing with colleagues, I can see that there is always a lot of confusion there. Yeah. Okay?
So the ICD, of course, is only when you have at least two neon atoms.
Yes. Yeah. But yeah, that physically that's you need two neon. Now I'm going to focus on the theory part just to get the equation, and this doesn't really matter. You have to see that as one state, this M star. Okay? So this is M star, this is M star. For all purposes, everything is just M star going to M plus plus an electron.
And it is M star, the first one, because it's not the ground state.
Yes, exactly. Yeah. Yeah.
You chose there the 1s1 and then the rest of the configuration. In the second case, you chose 2s1
Yes.
and not 1s1. That choice is deliberate.
Yes. So why? Because if you make a hole in the 2s, you cannot have Auger. You don't have enough energy to emit a second electron. So this is not. If you have only one atom, okay, and you make a hole here, you ionize this one. This is not a resonance. This is just an excited state of neon plus, and it's below the ionization potential of neon plus. So it's below this energy there. So it's not a resonance. So it's some states that are here. Okay? And here I decided to put 2s1 first because if you have a neighbor, now your state is here. And then it can decay. Okay? And I didn't include 1s. I mean, it's also true if you make a hole in 1s, but if you make a hole in 1s, you're going to see mostly Auger and not ICD. So it's possible. It's still a path. It's still a channel, actually, that should be considered, but it's a weak one.
Because local OJ is a local within the
Yeah. So it's
will be stronger than
yes. But it's actually a good example. So I'm going to take it. I'm going to use. I didn't plan to do it, but let's do that. So I have neon plus 1s1, 2s2, 2p6. I have a neighbor. So this is good. It's going to help me to illustrate. I didn't know how to do it. So thanks, Shiva. You have two ways now. You have Auger, where you get neon plus plus 1s2, 2s2, 2p4 neon plus an electron. Or you have ICD, which is neon plus plus an electron. Okay? And those are two different channels. Okay? I'll explain what is, what I mean by channels, but it's just different possible decay process. The same resonance. Okay? And the width of the resonance, okay, is the sum of the width of those two guys. Okay? So, or you can say that the lifetime, or the inverse of the lifetime, is the sum of the inverse of the lifetime of this guy and this guy. Okay? So if you sum the two width, you get the total width. And if you inverse the total width, you get the lifetime. Okay? So if neon plus with the hole in 1s as a neighbor, the lifetime would be shorter. Because you can have OG and ICD. It's like you take a bathtub, you have a hole, then it will leak through the hole. You make two holes, it leaks faster. Okay? And in that case, you should see OG like a big hole because it goes fast, and ICD as a smaller one. Okay.
The point also you're making is that from the neon dication,
Yeah.
The final state that you wrote for the ICD, any plus electron will be the system will relax to that.
It could be. Yeah, it could.
Okay, the width is not due to that. Is it?
No, that's a second step.
The mere fact that you have two processes is enough to change the
Yes. It can get complicated if for example, if exactly this guy then can go to this guy. Yeah. And if the time it takes to go from here to here is as fast as this guy, then it's very complicated. You have to include everything.
So again, coming back to the discussion on Fano, if two pathways led us to the ICD products,
But here their distribution.
sorry. No, here, that's the point I was trying to make. So here, if we had two pathways leading to the same ICD product, that line shape should have been this Fano.
It depends what you measure. It's always depending on what you measure.
In principle, the dication plus the neutral can also lead us to the same product.
Yes.
Plus.
Yes.
But then we can, as Arvind is pointing out, we can distinguish the two pathways. So we will not see a Fano profile in this
Yeah.
case, despite the fact that we could have that product.
Yeah. Yeah. No, you're right. Yeah, you're right. Yeah. All right. So it's good for resonances? Okay. It's clear. Because now we're going into a bit of math, but it's really trivial. But I wanted to just illustrate with some drawing. So how do you write your resonances? So you need an ansatz again for the wave function. And so I'm going to write it like this. So you have your wave function here for this excited, for your resonances. Oh, no, I shouldn't take M star. I should call it resonances. That depends on the energy. And I'm going to write it as a bound part plus a sum over the channel. Then you have a continuum, so you have P, beta. Okay, so let me explain. So that's your solution of your Schrödinger equation for the continuum, in the continuum. Okay, and you write it as a bound part. So that's what I drew. This M star, okay, that is quasi-bound. It looks like an excited state. So you have this, and you have the continuum. That has the same energy, okay?